So can people online hear what's going on here in the room? Okay, great. Just two tabs. Okay, thank you. Okay. Well, today we're happy to have our own Osamu to give us a seminar. He is currently an ASP postdoc, and prior to joining NCAR, he got his PhD from University of Chicago and then bachelor's degree from UIUC. His research focuses on understanding and scrutinizing the climate model projection of anthropogenic climate change through using a lot of simple theories, experiments, and observations. And he is interested in a wide range of topics such as heat extremes, climate, large-scale dynamics, convection, etc. He's going to talk to us about the surface temperature extremes over land in a warmer climate today. Let's welcome today's speaker, Osamu.
So I'm coming up on the end of my postdoc appointment here. So I figured it would be a good idea to summarize, go over what I've been working on in the past 2 years. And even after I leave NCAR, I want to have this connection with the scientists here and potentially work on some of the questions that I would bring up today together. So that's the goal. I appreciate a lot of feedback, especially as I'm beginning to wrap this up into a paper. So this work is in collaboration with my mentors here at NCAR, Isla and Brian, in addition to collaborators outside, including Chin, who is a grad student at Purdue, visited here, and that's how we got to work on this project together, and Karen, who's been providing a lot of the statistics expertise for this project. So it's going to be about work at 5 days, and I just want to start off with this background of the warming of mean days. This is one of the most canonical, I think, problems that climate scientists strive to understand, right? This spatial pattern of mean warming in a future climate. This is following SSP 370 at 2 degrees global mean warming. And regardless of what forcing you use, you generally get this robust pattern of amplified warming in the Arctic and over land. And this is robust going back all the way to Manabe's first GCM simulations to today's complex Earth system model. So we have a pretty good understanding of what the mean spatial pattern of warming looks like. But arguably, what matters for society is not necessarily the change in the mean, but the change in extreme, in particular, the hot end of the extremes. So we can think of examples like the impact of heat extremes on human physiology and human health. You can see these temperatures we saw in the Pacific Northwest heat wave in 2021 was very impactful and led to thousands of deaths. We know here, living here, that heat extremes also impacts wildfires and also for things like crop failure and droughts. So heat extremes are important to understand. And so what does heat extremes look like, the change in heat extremes in the future climate? So this is the analogous warming pattern for if you just look at days that exceed the 95th percentile, just over the annual mean for sampling all months. And so we generally see similar behavior, largest warming in the Arctic and amplification over land. But if I flip back and forth between the mean warming here and hot day warming, you might see that there's some differences in the pattern of magnitude of warming. So if we take the difference to see this a little more clearly, it says the warming of hot days minus the warming of mean days, annual mean. And we see a very clear structural pattern here where in the high latitudes, we see a suppression of warming on hot days relative to mean warming. It still warms, of course, but there's less warming than the mean. And in the tropics, you generally see amplification. These colors are indicating where reds are where you have more warming for the hot days than the mean, and the blues are where you see the suppression of warming of hot days. So I'll refer to this differential warming in the positive sense of hot days relative to the mean, amplified hot day warming moving forward. This specifically in the tropics, this amplification of hot day warming has been studied. It's not something that's new. Mike Burns' work from 2021, for example, shows this in a tropically aggregated sense. So if you look at all the grid points, equatorward of 20 degrees, and compare the warming of the mean all the way to the left and gradually subsetting to the hotter and hotter days by the percentile of the day, you see that there's more warming. This upward tilt that you see in the red line shows that there's more warming on hot days relative to the mean. And these dashed lines are what you get if you use simple theory, assuming convective quasi-equilibrium and moist convective adjustment. I won't get into the details there, but that's one way to explain why you get amplified hot day warming from an atmospheric dynamics point of view. We also see that this is really a land only feature. The amplification exists over the ocean, but it's very weak. And so if you look at the spatial pattern, this has also been studied by, for example, Suchin's work and many others. I'm just showing this to indicate that this pattern, this behavior of hot days warming more than the mean, is robust. This study used a slightly different variable, the daily maximum temperature, instead of the daily mean temperature that I've shown in the past few slides. And she's also looking at the top 20 percentile for hot days, where I showed the top 5 percentile. So regardless of what kind of metric you use, this amplification of hot day warming is robust behavior. And this is also from CMIP 5 simulations, where I was looking at CMIP 6 simulations before. So it's robust in many ways, in terms of metrics, in terms of the generation of climate models. This is happening. So what do we still not know about this problem then? The first thing is the seasonal cycle. So I showed you the annual mean, and Mike Burns' work focused on the annual mean. And Suchin's work and many others that think about this problem focus on summertime change. Understandably, that's when the impacts are going to be the greatest. But I think it's still important and useful to quantify, and then understand if there is a seasonal cycle, what leads to that structure across time. And the other thing is regional hotspots. So a lot of studies have focused on specific regions around the globe, and when it goes into a lot of detail, for example, Europe is a big study area that there's a lot of literature on. But globally, if you want to think about why there are hotspots of amplified hot day warming emerge, there aren't that many papers that go into the mechanisms of why the hotspots emerge. So these are the two research questions. What's the seasonal cycle, and what gives rise to these regional hotspots? Starting with the seasonal cycle, first of all, does the seasonal cycle matter at all? So the left panel, I'm showing the annual mean signal that I showed before. And the right panel, I'm showing you the seasonal amplitude. So this is the maximum signal, the same variable computed over the season, over each month, and taking the maximum of whatever the month it happens and the minimum. And that difference is I'm quantifying as the seasonal amplitude. And if you look at the color bar, it's the same magnitude for the color bar scale. We're seeing that the signal for the annual mean is comparable to the signal of the seasonal amplitude, indicating that even in regions where we have a large signal, like in the tropics, it's indicating that this amplification is concentrated during some time of the year. And another way to think about it is in regions where you don't have as much of a signal, like in most of the United States, there's still a large seasonal cycle indicated by the seasonal amplitude, which suggests that if you look at the annual mean, it's the cancellation of different signals, positive or negative amplification of hot days happening through the seasonal cycle. So the takeaway here is that the seasonal cycle is important. The magnitude of the seasonal cycle is as large as the annual signal itself. Now, going back to focusing on the tropics again as a start, what is the seasonal cycle? So this is when I average grid points equatorward of 30 degrees. And on the x-axis, I'm showing you month relative to the winter solstice. So this allows us to combine northern hemisphere and southern hemisphere grid points together and have a sense of the seasonal cycle that's relative to when the insolation is maximum. So we're looking at amplified hot day warming on the Y and this month relative to the winter solstice on the X. And it is very robust seasonal cycle where the amplification peaks in summer. That's kind of the worst case scenario from an impact point of view. And it's a nice thing, I suppose, that so many studies have focused on summertime change because that is when the change is largest. But why does it amplify the most in summer? That's an open question. So one way to think about this problem, we're talking about near surface temperature. So one very natural way to think about this is from the surface energy budget. Surface energy budget, the near surface temperature, TA, appears as one of the variables that heavily influences the surface energy budget. Other variables that we need to think about include atmospheric humidity, Q, the land surface temperature, TS, and soil moisture, SN. So in an equilibrium sense, the surface energy budget is really just composed of three categories of terms. Radiative heating, that's the net solar heating minus long wave cooling. And then two other cooling terms, generally cooling, sensible and latent heat fluxes, which depend on, first order, on the magnitude of the temperature and moisture gradients, respectively, between the land and atmosphere. And one of the consequences of climate change, this doesn't happen everywhere, but in many cases, you get larger volatility in precipitation, meaning that you have heavier bursts of rain interspersed by longer dry spells. And when that happens, more of that rain goes into runoff instead of draining or moistening the soil. So when that happens, soil moisture, the land dries out. And you have a decrease in the gradient between moisture in land and atmosphere, so you get a reduction in latent heat flux or a reduction in evaporative cooling of the ground. And when that happens, you still have to maintain energy balance, and what balances, or what's been hypothesized to balance this, is an enhancement in sensible cooling of the ground, which acts to heat the atmosphere. So the idea is this repartitioning of surface turbulent fluxes is larger in hot days than in the mean, which gives rise to an amplification in temperature on hot days. So this idea has been shown to work really well for the summertime spatial pattern in the previous generation of models, again by Sachin's work. Left panel showing amplified hot day warming. This is what I showed before. The middle panel showing the hot day amplified hot day sensible heat flux change. So this is sensible heat flux change on hot days minus 3 days. And we see that there's a very good positive correlation. The hot spots where we see amplified hot day warming are also where you see amplified increase in sensible cooling on hot days. And this is coincident or attendant with the change in evaporative cooling, a decrease in evaporative cooling that's amplified on hot days relative to the mean. So the schematic picture that I showed in the previous slide is borne out in these CMIP simulations and works really well. This positive correlation for temperature and sensible heat flux, and this negative correlation between temperature and evaporative cooling. Does the same mechanism or idea work for the seasonal cycle? So if you look now at the evaporative cooling, amplified hot day evaporative cooling, now on the y-axis, as a function of months since winter solstice on the x, we see that this decrease in evaporative cooling on hot days is most pronounced during summer. That's consistent with what we saw with temperature, so that's a good sign. And most, like Sachin's work just went into evaporative cooling changes or latent heat flux changes. But I think it's useful and important to go a step further. Why is there this decrease in evaporative cooling that's so strong during summertime, but not so in the rest of the season? Let's go back to the schematic. We said that soil moisture is one ingredient or one variable that influences evaporative cooling. So what exactly is this relationship between evaporative cooling and soil moisture change? So another one of Sachin's work has shown this relationship between latent heat flux and soil moisture. This is just taken from one grid point in southern Africa. Each dot is 1 day, and
these colors are showing the precipitation for that day. And it looks kind of messy, but she argues that there are these different regimes of soil moisture, latent heat flux, and soil moisture relationships that has these 4 different segments, where if you're in the extremely dry regime, then no matter a small perturbation in soil moisture just isn't going to lead to an enhancement in latent heat flux, because that moisture is just too tightly bound to the soil, or is not concentrated to, is not available close to the atmosphere where it can evaporate. So this is where, like in a desert, for example, even if you have a small change in soil moisture, you just won't get an increase in evaporative cooling. At some point, you get this regime where things are intuitive, like I mentioned before in the schematic, that evaporative cooling acts on the gradient of moisture between the land and atmosphere. So the higher the soil moisture of the ground, the larger the gradient between the moisture of land and atmosphere. And this transitional regime is depicting that intuitive regime, where you're just increasing the gradient in the moisture between land and atmosphere. But this doesn't continue forever. At some point, that schematic also showed that you need to have some heating source to even have a cooling in the first place. And so at some point, as we get into really moist days where it's starting to rain and it's cloudy, you get less radiative heating. So it no longer becomes limited by how much moisture you have in the ground, but how much energy you're receiving at the ground from radiative heating. And so that's when you transition from, and that transition between what we call water limited hydroclimate regime to an energy limited hydroclimate regime is demarcated by the critical soil moisture. And if you really go in further into the wet regime, the active rain regime, that's when the atmosphere starts to get saturated. So you get less and less evaporative cooling until it's 100% saturated and you just cannot evaporate from the surface. So that's why it tapers down to 0 at the very right end of the schematic. And so that was one sort of qualitative way to understand the relationship between latent heat flux and soil moisture. Sue and Diermeyer approach this from a more quantitative perspective, where they take all these data, these variation across days in the latent heat flux and soil moisture, and fit this piecewise linear relationship to it. And we can test out different candidates for the piecewise linear line. Maybe someday in a region where you have a lot of variation in soil moisture and hydroclimate, you might fit an entire 3-segment line, or in regions that are completely wet, and like in the tropical rainforest, you might not ever be in the water limited regime. So we test out, we can fit these different candidates depending on whatever data we have, and we can then evaluate how well we can reproduce the evaporative cooling change inferred by this very simple piecewise linear fit, and input in this line the soil moisture change and see how well it reproduces the actual evaporative cooling. So that's what I'm showing here now. The black line is the evaporative cooling response on hot days minus the mean. As I showed before, it had this minimum in summertime, and this blue line I'm now showing is the reproduction of evaporative change when you just use this piecewise linear relationship. And it does a pretty good job with capturing this really pronounced peak during summertime. And it's really helpful that this line works to explain the evaporative cooling response, because now we can play around with it and modify things with the calculation to test some ideas of what matters and what might not matter. The first thing is, the line that I showed you before accounts for how this fit can be different in a future climate. So I'm showing you here in one grid point, again in Southern Africa. The blue line is I'll just call this line the Boudical curve. It's technically not, because the Boudical curve uses non-dimensional numbers. This is dimensional. But I'm just going to call it the Boudical curve because it's very similar in concept. And so the blue Boudical curve is drawn using historical data, which is defining as 1980 to 2000. And the orange line is doing the same thing, but temperature data. And this is centered around 2 degrees global mean warming. And we see that there is a slight difference in just where the line is positioned and also the slope of this transition regime. So some of these changes are telling us that the sensitivity of evaporative cooling to soil moisture is state dependent, and that other things that latent heat flux depends on, like the humidity and vapor pressure deficit, the wind in the atmosphere, may also be a function of the hydroclimate or the soil moisture anomalies, so it can alter these lines. Another thing that I haven't really talked about is all the like how plants take up the moisture in the soil and can transpire it instead of evaporate, also can affect the steepness of this line. So all these things can lead to, all the changes in these mechanisms can lead to a change in the slope, and thus make a difference in terms of how this sensitivity of evaporative cooling to soil moisture can be state dependent. I keep saying evaporative cooling, but it's evapotranspiration. It's the total evaporation and transpiration. Okay, so one thing that we can ask is, okay, it looks kind of small, this change. So what happens if we ignore the climate dependence of this Boudical curve? So what I mean is, if you now calculate the change only following the historical Boudical curve, ignoring how it could change in the future climate, you get this dashed blue line. So clearly, if you want to understand the quantitative response of evaporative cooling change, you need to account for how this Boudical curve changes in the future climate. But we can still understand the seasonal cycle, for the most part, just using the historical Boudical curve. And the reason for that is just this dashed line is basically just the solid line that's shifted up. So it still captures the summertime minimum. And so we're going to proceed now using this historical only Boudical curve to further dissect different mechanisms that could lead to this summertime minimum in amplified hot day evaporative cooling. So one way that can lead to this amplification of evaporative cooling change on hot versus mean days is, say, if the hot day is in the water limited regime, left of this vertical dashed line, but the mean day is in this energy limited regime to the right of the dashed line. So when this happens, any sort of change in soil moisture for hot days will lead to a large change in evaporative cooling, whereas for any change in soil moisture that happens on mean days will lead to very little changes in evaporative cooling. So that's a very easy way to understand how you can arrive, an amplified response for hot days can arise relative to the mean. Another pathway is that they're both hot and mean days are both in the water limited regime. It's just that the soil moisture change is amplified on hot days relative to the mean. These are the two ways you can think of amplification happening if you just focus on the historical Boudical curve. And we can test which pathway matters by doing a simple calculation where, the actual calculation that I showed before, I'm putting in the actual soil moisture change on hot days and the actual soil moisture change on mean days. Well, we can do this alternative calculation called non-amplified soil moisture change, where I just prescribe the same exact soil moisture change for hot days as in the mean days. And now we can see that if this seasonal cycle is arising due to an amplification in soil moisture decrease on hot days that is summertime only, then our signal that we saw before should disappear in this non-amplified soil moisture calculation. But it does alter this non-amplified soil moisture calculation, does significantly alter the seasonal cycle, but this summertime minimum still remains even after you remove this amplification in soil moisture on hot days relative to the mean. So the way I interpret this result is that if you aggregate all the data in the tropics together, this amplification of evaporative cooling change on hot versus mean days happens because that hot and mean days are on different hydroclimate regimes. Hot days are in the sensitive regime, the water limited regime, and mean days are in this insensitive regime, the energy limited regime. And we can further just sanity check this by actually looking at the soil moisture, seasonal cycle of soil moisture. I'm just showing you again this amplified hot day warming signal that I showed you a few slides back on the left. And on the right, I'm showing you the soil moisture seasonal cycle relative to the critical soil moisture. And so this 0 is on the dashed line. So wherever you're below the dashed line indicates you're in the water limited regime. And wherever you're above, is the energy limited regime. And the black line is showing the mean seasonal cycle of soil moisture for mean days, and red is hot days. So consistent with this pathway 1, you get amplification during summertime because it's the time of the year when you have this dichotomy of mean days being energy limited and hot days being water limited. The rest of the year, they're both mean and hot days are in the water limited, so they behave rather similarly and you don't get as much of an amplification. So that's the tropics and the seasonal cycle for the amplified hot day warming in the tropics. Let's move on to the spatial pattern. So we saw that it peaks during summertime in the seasonal cycle. Is this robust? Like, if we now move on to this spatial pattern, we want to know whether the aggregated seasonal cycle actually kind of is reflective of what's happening in space. And so this plot is showing what time of the year the maximum amplification happens in the tropics. Wherever it's red indicates that the maximum happens during summer, which I define as JJA and DJF, respectively, for the north and southern hemisphere. Wherever it's white is equinox, and wherever it's blue is winter. And so it's a little bit messy. It's not red everywhere. It's important to keep that in mind. But majority of there's a plurality of summertime maximum happening. Equinox also being important, especially near the equator, and some places that maximize during winter. But because of the prevalence of summertime maximum happening generally, I'm just going to focus on the summertime for moving forward. And so if you focus on the warming of summertime and look at the spatial pattern of amplified hot day warming, this is similar to what we already saw in Suchin's figure. We see that there are 4 hotspots. There's a Southeast Asia hotspot, South America hotspot, a Sahel, and Southern Africa hotspots. So what gives rise to these hotspots? And first thing we can try is do the same exact thing that Suchin did, comparing this map of warming to evaporative cooling change. So this is the associated evaporative cooling change relative for hot days relative to mean. And we see that these same hotspots in temperature are also hotspots in evaporative cooling decrease in summertime. Let's repeat the same exact train of thought of using the Boudical curve to see if we can explain these hotspots. So doing the same kind of fits, grid point by grid points. And so the bottom panel now shows the evaporative cooling change for hot minus mean days derived using the Boudical curve. And we see a very good reproduction of the actual evaporative cooling change on the top. And so now let's see, same exact thing. Let's see if the change in the Boudical curve in a warmer climate matters for explaining these hotspots. So the top shows the calculation including the Boudical curve change, and the bottom shows the calculation when you only use the historical Boudical curve. So of course, as we saw as well in the tropically aggregated response, for understanding things quantitatively, the change in the Boudical curve matters. We see a general decrease in the response if you only use the historical Boudical curve on the bottom, but you still capture at least the sign of the change correctly, even if you use the historical Boudical curve. So let's proceed on again, and now look at what the non-amplified soil moisture calculation looks like. Again, that calculation will not lead to amplified hot day warming or amplified hot day evaporative cooling change if both the hot and mean days are in the water limited regime. And if you look at the non-amplified soil moisture calculation compared to the control actual calculation, you see that everywhere except for the Sahel, you can reproduce this decrease in evaporative cooling on hot days minus the mean. So this suggests that for these three regions, the Southeast Asia, South America, and Southern Africa, the tropically aggregated explanation that it was this dichotomy of the mean and hot days having different hydroclimate regimes applies, whereas the Sahel is this exceptional region where it's different. It's that it's that instead hot days and mean days are both water limited, and that in the Sahel, the reason why you get this amplified evaporative cooling response is because the soil moisture response is amplified. So this reveals that this explanation or the mechanism of what leads to evaporative cooling change amplified on hot days, which is then connected to warming, is different depending on which region you're talking about. So in this case, it's just one region, the Sahel, but I think it's useful to understand and know that the same response can arise from different mechanisms. And so I think it'll be useful to understand this, if you want to start to scrutinize model differences with observations and testing whether models are capturing the right predictions or responses for the right reasons. Okay, so I've been focusing on the tropics, where the tropics, it's very clearly this anti-correlation between warming and evaporative cooling seasonal cycle, as we see this blue everywhere. Let's talk next about the high latitudes, right? Extratropics. So if you look now at the extratropics, this clearly doesn't work. In many regions, especially go up to the very high latitudes, like polar to 50 degrees, you see an opposite correlation. You see a positive correlation between warming and evaporative cooling. So it's clearly not a repartitioning of surface turbulent fluxes of the air in the high latitudes. So if you then look at the amplified hot day warming seasonal cycle for the high latitudes, the amplification in summer is quite weak. Instead, you get a strong suppression. So this is the negative value is the strong suppression that's concentrated in autumn. So this explains why the very early figures I showed, there's a strong suppression of hot day warming in the high latitudes. This is really coming from the autumn season and the winter season, and not from the summertime. So this also shows that it's really important to think about the seasonal cycle of amplified hot day warming, and not just the annual mean. Another way to think about it is on the flip side, hot day warming is suppressed in high latitudes, but the cold day warming is amplified. So if you now look at the bottom 5 percentile of days, you see a large warming amplified in autumn. So it's like almost asymmetric hot and cold day warming. And the idea, this kind of problem is not new. A lot of people have thought about it. And instead of the repartitioning of surface turbulent fluxes, what people think is important in the high latitudes is instead atmospheric dynamics. So we all know, living here in the mid latitudes, that cold days generally mean the air is coming from the north, the Arctic air is coming down, whereas warm days generally mean southerlies, air coming from the tropics, which suggests that the spatial pattern of mean warming matters a lot for changes in extremes. Indeed, I think we all are familiar with this idea that warming is amplified or maximized in the high latitudes in the Arctic. It's very simple. If the warming is large in the north of where you are, then you're going to experience larger warming of cold days, where the source of the air in cold days is from the north, and less warming on hot days, where the source of the air is from the south. So if you now try to think about this more quantitatively, we can sort of express this idea of the temperature we experience being linked to advection of temperature meridionally from the north to the south, computing the temperature advection seasonal cycle, it's very consistent with the seasonal cycle of amplified hot day warming. So we're looking at 850 hectopascal meridional temperature advection, and this peaks as well in autumn for the cold days. So it's very consistent. And then if you look at the seasonal cycle across each grid point individually, you see generally a positive correlation between the seasonal cycle of amplified hot day warming and 850 hectopascal temperature advection. However, something that we're still working on and trying to understand is the spatial pattern, or the hotspots of amplified cold day warming, showing in the bottom. So it's quite messy, but maybe you could sort of say there were 3 hotspots if you focus on land. This Siberia hotspot, this like North America, Alaska, Canada hotspot, and Eastern Europe hotspot. And all of this is still hand wavy at this point. Maybe they're linked to zonal hotspots in Arctic amplification that happens upstream of these hotspots in sort of lower and high latitudes. And the reason why it's all hand wavy is, if I mentioned 850 hectopascal temperature advection earlier, if you look at the spatial map of temperature advection, it's not really aligned well with the warming. But maybe it's this like Wallerian perspective has limitations, and we need to think about Lagrange tracking. Perhaps that could work. If anyone has experience doing that, please let me know, and I'd love to apply whatever methods or tools you have to try to make this link more quantitative. Right now, we're just sort of hand waving. So that's I think that's the same thing. Okay, so that brings me to the end here. So the first takeaway is I think this is the first time that we're really digging into the seasonal cycle of heat extremes relative to the mean changes, and the seasonal cycle is important. The seasonal cycle amplitude is as big as the annual mean. So that's the first takeaway. The second takeaway is that in the tropics, this amplification peaks during summertime, and it's really consistent with changes in evaporative cooling. So the decrease in evaporative cooling on hot days, that's caused by different reasons or mechanisms depending on which region in the tropics you're looking at. And finally, in the high latitudes, we have amplification of cold days instead of hot days that peaks in autumn. And this seasonal cycle is very consistent with the seasonal cycle of Arctic amplification, and the fact that the cold days we get air from the north. And so it's very consistent with meridional temperature advection. But as I just mentioned, this works really well if you aggregate over space, but it doesn't explain too well the spatial pattern. So that's what I'm still working. I'll leave my 3 takeaways here, and I'm happy to take any questions.
We have plenty of time for questions. Oh, okay. So, Dave, maybe you can just unmute yourself.
Sorry, that wasn't a question, but nice talk.
All right. Yes, go ahead.
Thanks for that talk, Osamu. It was great. Osamu, sorry. For the spatial distribution in the high latitudes, have you tried relating it to the different plant types that occur regionally?
I haven't, no. What's your idea behind?
Just that in some places you have grasses, some places you have forests, and that might, instead of just thinking of atmospheric processes, the different land, in the different land types might have different radiative properties, the way they respond.
That's a good point. Yeah, I remember looking at the spatial map of radiative heating change, and there was some correlation there. So I think, yeah, what you're saying is definitely worth thinking about.
It's like Greenland stood out, and that has a very different surface type than what you see in other places. So.
Yeah, great idea. Yeah, I'll look into it.
So maybe in the same context to look at the snow on the land, because I mean how that's distributed and also how it's changing,
right?
In the warming climate, because you're looking at a time period, it's in the fall where you see the biggest signal. They're usually those regions are usually snow covered during that period of time, but exactly when they become snow covered is, there's some regional dependence to that. So in addition to the vegetation idea, I think snow on the ground would be another kind of element of that.
Yeah, snow is something we have thought about, and we're trying to quantify like snow in particular, because if you just look at CSM, there's a really good correlation or connection between temperature changes and the snow melt flux. Yeah, the problem is it's different. The number of variables, we have to work with daily variables, so that gives us a little bit of a limitation on what data we can use. So with CMIP data, we might have like snow thickness and fraction perhaps. So yeah, I'll think about what I can do with that. But yeah, snow for sure is important. Yeah. Yeah.
A similar context, should we expect any elevation dependence on this? I have no idea. I'm just asking.
Yeah, that's a good question. Yeah, I haven't thought about it too much. It definitely matters for me warming. Yeah, like in terms of yeah. I don't know how it affects hot days. Yeah, or cold days. Yeah.
Yeah, it was a great talk, and I wonder if you go back to your, I think it was the takeaway one slide.
Yeah.
The sort of description is that it's all very consistent until you get to East Antarctica, and I was wondering, is that like what's happening in East Antarctica that is different from the other high latitude, perennially snow-covered regions like Greenland or the very northernmost parts of the.
Yeah. Well, and I think part of it, I don't know if this is snow, but part of the general asymmetry between the north and south is there's like no amplification of warming, or it's really weak amplification in the southern hemisphere compared to the north. Are you referring, like, which part of Antarctica is east?
The sides, the
Like
red
both of
patches,
these, right?
basically.
Okay.
Yeah.
Yeah, I really don't know. So in all the seasonal cycle plots that I was showing, I actually exclude Greenland and Antarctica because they feel like kind of outliers or just completely different mechanisms. Yeah, I don't know.
If I understand correctly, you are actually trying to attribute like the different heat extremes to the different soil moisture content or different evaporative cooling over the land. But we know that they're like highly correlated. Like, do you try to attribute like a causal, like because of the evaporative cooling, and so that it contributes to the extreme heat over like certain land regions, where you're just trying to do like a correlation thing?
You mean like the Boudical curve is like an empirical relationship?
I mean, like, well, if you do like a lead lag thing, instead of doing like a co-located, do you observe like any like prior change in soil moisture that can actually lead to the later change in the surface, like temperature change?
Right, I see what you're saying. I did that at one point, but I can't remember off the top of my head.
Maybe the result is not that good.
Yeah, I think it was, the fact that we kind of moved away from it probably means that it was kind of messy and complicated. So I did look at like precip and evaporation changes prior to the hot day, and that seems to indicate it's really a decrease in precipitation and not so much like a change in evaporative demand, both of which could like influence soil moisture. And in the case of evaporation, it could even be that the temperature is driving changes in soil moisture.
Yes, that's what I'm thinking.
But the fact that precipitation seemed to be the driver there, I think makes it, it suggests that it's soil moisture to temperature, but I think I need to look at this a little more carefully and see if we can tease out the direction of causality. But
Yeah.
I feel like it's not. I think there's an element of both things, right?
Mhm.
There's also like simulations, like led by Claire Durakas. I forgot the last name, but that sort of allows us to maybe test these ideas. And I've reached out to her to look at those simulation results. So I think that could be one fruitful way to maybe quantify the causality or eliminate some of these feedbacks. Yeah.
Okay. Yeah, go ahead.
I'm really curious about the difference between Sahel and the other tropical regions, and potential influence of land cover change, because you looked at SP370, right?
Yeah.
So you might have deforestation in quite some areas in the tropics. And so I wondered, have you thought about what the contribution there could be to, for example, shifting regimes concerning the Butico curve?
Yeah, land use change is definitely another big thing that can influence the Butico curve change. Yet, I think the Sahel was that one region where if you just calculate using the historical only Butico curve, it's still like the same magnitude as one of the change. I think on the other hand, it seems like South America or the Amazon is a region where like maybe this difference in historical only and the future Butico curve was really strongly linked to deforestation. The Sahel, I don't know. Did you know that there's a large deforestation?
I would say I would agree, if I remember right, average implementation of deforestation in the different models, that in Amazon there is much stronger signal than in Sahel.
Oh, okay. So
that would be consistent.
Okay, interesting. Yeah, I'd love to look at like some metric of land use change. Maybe we can talk about what I can look at there. Yeah.
I have a question. So thank you for giving us such an interesting talk. My question is about, you are showing the seasonal dependence of the hot days in the tropical regions, but I think the peak appears in the summer season. But from my experience, because I know in Thailand the hottest season is April, because it's the equinox season. Otherwise, in your figure, the peak appears in the summer for the equatorial region.
Right. So I think part of the necessary ingredients for regions like Southeast Asia is that in order to get a relative amplified warming of hot versus mean days, the mean day has to be energy limited, not water limited. So the seasonal cycle is closely related to the seasonal cycle of precipitation, where the mean day is moist enough during the monsoon season that comes after the hot, dry April, month in Southeast Asia. So yeah, actually, from an impacts point of view, you're right that we should actually care more about the shoulder season, or like the spring that we think of as spring as the hottest season in the tropics. That would matter even more. Yeah.
You also look at these amplifications in terms of the dew point change.
Yeah.
Or heat index, or
right, like wet bulb temperature.
Yeah. What's the impact?
Right. And one of my co-authors, Chin, has thought about this thinking. I think maybe writing a paper on this. Yeah, so it's definitely being considered. Yeah.
Peter Lawrence has a comment. He said like SSP 3-7.0 has complete deforestation of the Congo. Peter, do you want to comment a little bit more on that?
No, not really. It was just following up on Felix's comment.
Okay, thank you. Okay, we got time for one last question. Go ahead.
Yeah, for me, just looking on this map, this sketch, looking in Africa and South America, more look at in terms of precipitation, like the Sahara region is more desertic, the rain it's throughout the year being having a constant rain or less rain, whereas in Southern Africa, when we have a decreasing trend of rain, mostly in Zimbabwe, Angola, where we can see that the color contrast of the blue, more precipitation should be taken into consideration when you're comparing two regions of Africa. Sahara being having a net constant precipitation, whereas Southern Africa there's that fluctuation. Whereas in South America, when we look at it, deforestation of Amazon could be one of the factors that need to be pointed out mostly when you look in this aspect.
Right. So I think in regard to contrast between the Sahara and Southern Africa, I think I didn't distinguish even within the water limited regime. There's two segments there, right? The transition and the completely dry regime. My guess, speculation is that the Sahara is completely dry, really, and Southern Africa gets enough rain that it's in the transition. So I think, yeah, it might be interesting to distinguish between those two different regimes within the water limited regime. And maybe we can further explain where you have any kind of signal, whereas like in Sahara, you get nothing. Yeah, a good point. Thanks.
All right, we are already on the top of the hour. Let's bring Osamu again.
Yes, there is. How about the ask Peter said? I don't know if that matters.
I like that. Okay.
I think I bring this vision.
The thing is, like regions that are very close to the equator, except for the southern South America, doesn't have like very warm signal.
Yeah, it's more the subtropics.
Yeah.
So it's not between tropics and subtropics.
It's almost, yeah, I think it'll be very interesting to understand the
Excuse me?